Course objectives. Let's take a look at some of the basic goals of this course. 1. You'll dive into the basics of logic design, focusing on essential gates like and, or, not, NAND, NOR, XOR, and XNOR, and how they contribute to creating digital circuits. The course will guide you through designing and analyzing combinational circuits using Boolean algebra and Karnaugh maps. Advanced topics include circuit design with NAND and NOR gates, understanding hazards in combinational circuits, and exploring flip-flops used in sequential circuit design. You'll also learn about Mealy and Morse sequential circuits, state equivalence, optimization techniques, key timing considerations, and the role of tri-state buffers. You'll be able to apply these principles effectively to design and optimize digital circuits. 2. Understand the basics of hardware description languages, HDLs, and how Verilog is used to design digital systems. You'll learn to describe hardware designs using Verilog's core language constructs, including module definition, design hierarchy, and behavior description. The course will also teach you how to synchronize and communicate between different parts of a design using Verilog. Additionally, you'll learn the rules for using identifiers, comments, and whitespace in Verilog code, ensuring you can effectively describe and configure simple designs. 3. You should be able to enhance RTL simulation efficiency and optimize design verification by adopting techniques that reduce simulation time and improve error detection. This involves understanding the balance between regression simulations and debugging simulations, as well as how RTL language elements impact simulation speed. By learning how simulators work, you can write Verilog code that uses RTL constructs designed for faster simulations. Additionally, adopting two-state simulation and random initialization techniques will help improve verification coverage while maintaining simulation performance. These methods will allow for faster simulations without compromising the quality of the debugging process. 4. You should be able to apply essential verification strategies to create verifiable RTL designs. This includes understanding and using key principles such as the fundamental verification principle, which focuses on reducing design complexity while improving verifiability through clear specifications. Another important concept is the retain useful information principle, which helps optimize the design process by preserving key assumptions and knowledge. Additionally, the orthogonal verification principle ensures the separation of verification concerns, enabling more efficient static verification. Lastly, the functional observation principle enhances verification by providing techniques for measuring functional behavior and increasing visibility in simulations. Embedding event monitors and assertion checkers in the RTL code will further strengthen verification coverage and observability. 5. You should be able to choose and apply different Verilog constructs for verification purposes. These include data types like real, real-time, and time, which are crucial for dealing with time-sensitive tasks. You will also be able to use case equality operators and which handle unknown or high impedance values. Procedural continuous assignments such as force and release allow for dynamic changes in signal behavior. Additionally, you can implement control flows using looping statements like forever, repeat, and while for flexible test scenarios. Event-driven simulation is made easier with named events, event, dash, and level-sensitive controls like wait. You'll know how to manage parallel execution with fork and join, and how to disable tasks or named blocks using disable. 6. You should be able to model a design using both behavioral and register transfer level, RTL, approaches. Behavioral modeling focuses on representing design functionality in a high-level, algorithmic manner without concern for hardware details like clocking. In contrast, RTL modeling is used to describe designs that will be synthesized into actual hardware, requiring accurate clocking, data storage in registers, and synthesis-compliant constructs. You will also gain an introduction to basic test benches, which are used to verify the behavior of designs in simulation. By understanding these concepts, you'll be able to model designs with varying levels of abstraction and create suitable test benches. 7. You should be able to use system tasks and functions to generate stimuli for simulations and to debug your Verilog designs. This includes displaying messages during simulation using $display, $write, $strobe, and $monitor. You can retrieve and format simulation time using $time, $stime, $realtime, and $time format. You will also learn to handle file input and output using $fopen, $fclose, and similar functions, as well as apply stimuli from memory files using $readmem and $readmem. Additionally, you should be able to control the simulation with $finish and $stop, pass real values through ports with $realtobits and $bitstorial, and retrieve command line arguments using $test plus args and $value plus args. Lastly, you will explore dumping value change data with $dumpvars and $dump ports and checkpointing simulations with $save and $restart. 8. You should be able to generate various types of test stimulus to verify and validate your designs effectively. This includes organizing the test bench structure, generating clocks, and creating different forms of stimulus such as inline stimulus, stimulus through loops, and stimulus using tasks. You will also explore generating random stimulus to cover unpredictable scenarios and applying stimulus from external files. Additionally, you should understand how to test corner cases and protocol interactions. These techniques are crucial for thoroughly exercising the functionality of your design under test and ensuring its robustness across different scenarios. 9. You should be able to optimize the development of test benches by applying effective strategies that reduce development time while maintaining flexibility. This includes understanding system-level verification, planning test strategies, and setting clear completion criteria. Additionally, you will develop reusable test benches by implementing self-checking tests and configuring the test environment with various methods such as scripts, source code constructs, and microcode. The goal is to create a test bench framework that not only automates testing but can also be adapted to different design scenarios, making it a valuable asset for continuous verification.